All right, let's look at using log rules to make derivatives easier. Suppose somebody asks you to find the derivative of this. Y equals ln of x squared over sine x. I said here with emphasis, it's highly preferable to use log rules to expand it first and then take the derivative. Here's why. I can take this and rewrite this as y equals ln of x squared minus ln of sine x. And let's go ahead and get rid of that exponent. I can rewrite this as 2 ln x minus ln sine x. And taking the derivative of this is easy. Y prime, the derivative of 2 natural log x is going to be 2 times 1 over x, or just 2 over x. Derivative of natural log of sine, the sine goes on the bottom. The derivative of sine goes on the top. And so we get y prime is 2 over x minus cosine over sine is cotan. So in just a few steps, we're able to get that. Compare that to this. I'm probably not going to finish this because this is going to be ugly. But the other thing we could do, we could say, okay, well, we've got a natural log, so we've got to put this downstairs. And then its derivative is going to go on top. And to take the derivative of that thing inside the log, we've got to use the quotient rule. So we get low d high minus high d low over low squared. Honestly, I was going to move that up, but I could just put the low squared down here. Sine squared x. So we could do that and then go through all the business of cleaning that up. But that's no fun. Using the logs over here makes this derivative so much easier. So let's do some more examples where using the log rules helps us out. Find the derivative of this thing. Now, finding the derivative of this would not be fun because if we didn't use the log rules, we'd have to put this on the bottom, and then we'd have to take the derivative of all this stuff on top. And that's a three-way product rule that we'd have to do. So it's highly preferable to rewrite this as, now I'm going to split this into three things here. We've got x cubed, we've got cosine x, and we got this. So I'm going to split this into natural log of, I could do x cubed, but I'm just going to go ahead and move that 3 down front. 3 ln x. And plus ln of cosine x. And plus, I could say ln of the square root of all this stuff. But instead, I'm going to go ahead and bring that 1/2 down front. So 1/2 ln of 3x squared plus 4. And now I can take all three of these derivatives really quickly. The first one is going to be 3 over x. The next one is going to be derivative of cosine. Cosine goes downstairs. Its derivative is negative sine. And then for the last one, we've got 1/2. I'm just going to continue this out as a fraction here. 1/2, the 3x squared plus 4 goes on bottom, and 6x goes on top. And so now I can do just a little bit to clean this up. Let's see, this we can't do anything to. This we can rewrite as minus tangent, and over here we can cancel the 6 and the 2, leave a 3 on top. So our derivative is 3 over x minus tan x, and then plus, let's see, we're left with 3x on top, and 3x squared plus 4 on bottom. So that's our answer for the derivative. And we're able to do that in a lot less space than if we didn't take advantage of the log rules. All right, one more. Well, a couple more. Find the derivative of this thing. All right, let's see. There's a couple of ways we could do this. We have some options here. We could rewrite this as 1/2 ln of the fraction. Or we could split it into natural log of 5x minus 9 over 1 minus x squared with the radical on both of them. And it doesn't matter which one you do. They'll both lead you to the same place. Let's actually go with this one. Okay, if I take that, then I've still got y equals, the top one becomes 1/2 ln of 5x minus 9. And the bottom one gives us minus 1/2 ln of 1 minus x squared. The only difference in these two is with this, I distributed I didn't distribute, I wrote it as a square root of the top over square root of the bottom. And then when I expand this out, I get a 1/2 on both of these. With this up here, if I expanded that out, we'd have 1/2, then we'd have natural log of 5x minus 9 minus natural log of 1 minus 2x. And we'd have to distribute that half across. So it would give us the same thing. All right, let's do this derivative. Y prime then is going to be over here, the 1/2. I'm going to put the 1 on top, the 2 on bottom. Then this is going to be 5x minus 9 under 5. Let's see, this is 1 minus x squared under negative 2x. So y prime is going to be, this first one's going to be 5 over 2 times 5x minus 9. And the other one is going to be, let's see, it's going to be plus because we got these two negatives. And then the 2's will cancel away. So we're just left with x on top and 1 minus x squared on bottom. All right, let's do this last one here. This would be a pain to do without using the log rules. But thanks to the log rules, we can expand this out, and this thing's going to be a piece of cake. So notice on top, we've got two things multiplied together. We've got x squared times e to the 2x. And on bottom, we've only got one thing. So I'm going to expand this into natural log of x squared plus natural log of e to the 2x minus natural log of x squared plus 1. That's not all on the screen. There, that works. All right, and so that's still equal to 2 ln x. Let's see, bringing that down front. This ln e to the 2x, that's just 2x. There are two different ways you can think about that. You could either say, oh, the ln and the e undo each other and it gives you 2x. Or you could bring the 2x down front times the ln of e, and then ln of e is just 1. So I'm not going to write it. I'm just going to write it as 2x. And then minus, nothing to do there, ln of x squared plus 1. So my y prime then is going to be 2 over x. Derivative of that's just 2. And then the natural log down there, we get x squared plus 1 under 2x. And there's not really anything we can do to simplify that, so I'm just going to circle that and let that be my answer. So I always joke with people that in calculus, things are the opposite of in pre-calculus, because here logarithms are actually making your life easier instead of harder. Let's see, that's the last example in this section. So I want to stop this video and we'll do the next section, the next part of this section on logarithmic differentiation. We'll do that next.